Hello everyone, this is Dr. Tasaduk Hussain yet again with the another lecture that I'm ready. So today's lecture will be about the achievements that the Bohr's model of an atom had. So we'll start right away. So the important achievements that the Bohr's model of atom had. So the first achievement that the Bohr's model of atom had was that it was able to explain the stability of an atom. Stability of an atom. So we knew that from the Rutherford's atomic model it had an important limitation, that was the stability of an atom. So according to Bohr's model, the electron does not lose energy as long as it is revolving in a particular orbit. So if an electron is revolving in a particular orbit, it's not losing any energy. Also, it cannot jump from the first orbit to a lower orbit. So this means that if an electron is in the first orbit, it's not supposed to go again somewhere downwards towards the nucleus, because it's the first orbit wherein it's always going to stay. So there is in short we can say that there is no gradual loss of energy by an electron from the first atomic orbital. Hence an atom is stable. So Bohr's model was able to explain this stability. Secondly, the Bohr's model was able to explain the emission spectra. Emission spectrum. So if we suppose we take an element and we heat the element. So if we take any element and we heat the element, so upon heating, what happens is all the electrons that are in the element, they gain energy or they absorb energy. They kind of absorb energy, or the electrons, they absorb energy and they start jumping from lower energy levels to a higher energy level. So if I give heat to any element, so the electrons will start jumping from lower energy level to a higher energy level because they gain energy. However, when an electron reaches to a higher energy level, maybe N2 higher energy level, so what happens is at that stage the electron becomes itself unstable. Okay, so once an electron is unstable, it starts to jump back to its normal level or a lower energy level. So in that case, what happens is some amount of energy that was earlier absorbed by the electron to go to the higher energy level, that energy is released back in the form of an electromagnetic radiation. And this process happens within fractions of seconds. So in 10⁻⁻⁵ seconds, the electron jumps back from the higher orbital to a lower orbital and releases energy. This energy is released in the form of an emission spectrum. So that's why Bohr's model was able to explain the emission spectra. So we can find that Bohr's atomic model clearly explains the origin of the emission spectrum, and it's clearly able to explain how this emission spectrum comes into process. Thirdly, there is one more process that we call as the absorption spectrum. Absorption spectrum. This absorption spectrum, in the same manner as we have the emission spectra, in a similar manner we have the absorption spectra. So the absorption spectra, this one is the emission spectra wherein energy is released, and this one is the absorption spectra, because here energy is supposed to be absorbed by an electron, only then it's going to an higher energy level. So if we pass an electromagnetic radiation through a solution of a substance, so if we have a solution of a substance somewhere here and we pass electromagnetic radiation through this substance, so what happens is we are passing this electromagnetic radiation through this substance, any substance, it can be a gas or anything else. So some of the wavelengths of this radiation are absorbed by this substance. So some of the wavelengths are going to be absorbed by this substance, and the wavelengths that are absorbed by this substance, they are characteristic of that substance. It depends upon the substance how many different wavelengths it is going to absorb. And this electromagnetic spectrum, then when you observe this electromagnetic spectrum on the other side of this substance, you see that some of the photons are missing from the electromagnetic radiation which were already absorbed by this substance. So if this electromagnetic radiation contains a few different types of radiations, as we know that electromagnetic spectrum has the visible range, ultraviolet range, infrared range, and all other radiations with it. So some of the radiations you will see from the spectrum, they are missing. So these regions wherein this radiation is missing, I'll be showing one of the diagrams on the top right corner, where you can see that there are black spots. So these black spots wherein you don't find any lines, you can see that that region actually becomes the absorption spectra, while as the lines where you see the fluorescent lines, that's an emission spectra actually. So the absorption spectrum is clearly explained by Bohr's model, and the dark lines that appear in the spectrum are basically the absorption spectrum. So we can say that the Bohr's atomic model was clearly able to explain the absorption spectrum also. Fourth achievement of Bohr's atomic model was that it was able to explain the emission spectra of hydrogen atom or hydrogen-like species, that is helium monovalent positive, lithium divalent positive, beryllium trivalent positive, etc., because all of these species contain one electron only. So Bohr's model of atom is able to give us the emission spectra of hydrogen atom or hydrogen-like species. So this is also an achievement of Bohr's model of an atom. However, we'll be studying it as an emission spectra of hydrogen atom or Bohr's model of an hydrogen atom in that terms. So if electronic discharge or electromagnetic radiation is passed through a hydrogen gas, so suppose this is hydrogen gas in a chamber and I'm passing through an electromagnetic radiation in the form of an energy. Electromagnetic radiation is passing through this tube, and this tube is filled with the hydrogen gas at very low pressure. So in that case, what happens is the atoms are supposed to be absorbing the energy from this radiation, and once they absorb the radiation, the molecules of this gas are going to break into smaller atoms, and those atoms absorb energy from the electric discharge that we pass through this chamber, and the electrons present in the first energy level are going to jump from, so if an electron is on a first energy level, it's going to jump from first energy level to a second energy level or to a higher energy level, depending upon the amount of energy that it absorbed. Similarly, the electron is then going to come back to its ground state, because in that case it is going to release some energy, which is a radiation emission spectra that I already mentioned. So when an electron jumps from lower energy level to higher energy level, it is absorbing energy that comes from this radiation, and when an electron jumps from a higher energy level to a lower energy level, in that case what happens is you will see that an electron jumps in a fraction of second that I already mentioned, 10⁵ seconds, it comes back to the ground level and releases an radiation. So this emission that comes from this experiment, you can see there is a kind of bluish glow actually. In the original experiment you will see that there is a bluish glow that's obtained on this side of the chamber, and that glow, when you analyze through a prism, so if this radiation is coming out here or the emission spectra is coming from here, and when you observe it under a prism, so this is a prism, you are passing this radiation through a prism, so what you see is that you obtain a group of different spectral lines. So you obtain a group of different spectral lines. So these spectral lines, you will see, they are obtained in different regions of the electromagnetic spectrum. So these spectral lines can be in ultraviolet region, they can be in the infrared region, they can be in far infrared region, or they can be in visible region. Okay, so this group of spectral lines is actually known as the emission spectra of hydrogen, because we are using hydrogen gas in this low pressurized discharge tube or chamber. So right now at this point of time, we know that the spectral lines are divided into different series, and those series we call them as spectral series. So in this series, these series are named after their discoverers. So whosoever discovered this series, the name comes after the discoverer. And there are 5 different series that we are going to study in the Bohr's emission spectra of hydrogen atom. So the first one is the Lyman series, and then the second one is the Balmer series, then it's Pascal series, Brackett series, and Fund series, all named after their discoverers. So now we will go one by one and see what the Lyman, Balmer, Pascal, Brackett, P-Fund series are. First, we'll go through Lyman series. Lyman series was discovered in 1915 by Lyman, and it appears in the ultraviolet region of the spectrum. It appears in the ultraviolet region of the electromagnetic spectrum, and the wavelengths of the different spectral lines of this series will be mentioned here. So the different wavelengths are in which these spectral lines, I'll be mentioning them in angstroms. So the lowest one is 912 angstrom, and then it comes 931 angstrom, 938 angstrom, so on so forth, and 1216 is the maximum wavelength that's obtained in this case. So the minimum wavelength is 912. It's very important from the examination point of view, minimum, and the maximum wavelength that's obtained is 1216. So you will see that in case of Lyman, what happens is the electron basically jumps from an energy level, 8th energy level. In this case, you can see it's jumping from 8th energy level or 8th orbit to an orbit which is 1. So basically, whenever an electron jumps from a higher energy orbit always to the first energy level, that case of spectral series is always known as the Lyman series, and it lies in the UV region. So that means from n infinity to n1, so from n infinity, from any nth orbital, if an electron always comes to the first energy level of an atom, so that case is always going to generate Lyman series. Similarly, in case of Balmer series was the first series to be discovered, because this series lies in the visible region. So this series was discovered in 1896 by Balmer, and this series it appears in the visible region. Balmer series in the visible region, and the different wavelengths that are associated with the Balmer series are: the minimum is 3668 angstrom, the minimum wavelength that's obtainable from this. Similarly, then the second one is 3970 and 4101, so on so forth, and the maximum wavelength that's obtained in this case is 6563. So this is max and this is minimum. Okay, so it's going to be always n8 or n infinity. Here also n infinity, any higher energy orbital, to always the second energy orbit. Okay, so this series is the Balmer series. In a similar manner, then there is the one more series, we call it as Pascal series. Pascal series was discovered in 1896, and this series appears in the near infrared region. It appears in the near infrared region. Okay, and the minimum wavelength that's obtained in this Pascal series is 8207 angstrom, and then 10050 angstrom, so on so forth, and we get the final 18751 angstrom. This is the maximum wavelength that's obtained in this case, and this is the minimum wavelength that's obtained in case of Pascal series. And in case of Pascal series, the electron always jumps from higher energy orbital, which can be any orbital up to the infinity level, and in our case we are showing up to the n8th level. So I can say that electron in this case is jumping from n is equal to 8th level, it always jumps to the 3rd level, so n is equal to 3. So whenever an electron jumps to the 3rd level, we say that there's a Pascal series in case of the emission spectra. Again, then there is this 4th series, which is known as the Brackett series. Brackett series was discovered in 1896 by Balmer, and this series appears in the near infrared region. It appears in the near infrared region. Okay, and the minimum wavelength that's obtained in this Pascal series is 8207 angstrom, and then 10050 angstrom, so on so forth, and we get the final 18751 angstrom. This is the maximum wavelength that's obtained in this case, and this is the minimum wavelength that's obtained in case of Pascal series. And in case of Pascal series, the electron always jumps from higher energy orbital, which can be any orbital up to the infinity level, and in our case we are showing up to the n8th level. So Brackett series. So this Brackett series, it was discovered by Brackett in 1922, and this appears in the Brackett series appears in the far infrared. So this is a near infrared, this is in far infrared region of the electromagnetic spectrum. So the wavelengths that are obtained in case of the Brackett series are four different spectral lines. So the first one has an wavelength of 14590 angstrom, so on and so forth, and the maximum one that is here is 40570 angstrom. So this is the minimum wavelength that's obtained in this case, and this is the maximum wavelength that's obtained in this Brackett series. And an electron always jumps from n infinity, or we can say in our case from n8th orbital to n4. So whenever an electron jumps to the fourth orbit or fourth shell from the higher energy levels or any higher orbit, so in that case the series is always going to be the Brackett emission series. And the last one is the Fund series. So Fund series was discovered by Fund in 1925, and this series lies in the it also lies in the far infrared region. It also lies in the far infrared region, and this series has three different spectral lines, as you can see, 1, 2, 3 in our case. So in that case, what happens is the minimum wavelength that's obtained is 22810 angstrom, and the maximum wavelength that's obtained is it's a 74800 angstrom. And in this case, an electron always jumps from n8th orbital, it always jumps to the 5th orbit of an atom, especially the hydrogen atom, 5th orbit of the atom. So this jumps in the 4th, this jumps to the 3rd, and this jumps to the 5th orbit. These are different spectral series that Bohr's model was able to explain. Now we are going to understand how we can calculate the energy that is associated or the wavelengths that are associated with these Lehman, Balmer, Pascal, Brackett and Fund series. So if we suppose that an electron is jumping from any nth orbital, from a higher energy orbital to some nth orbital which is in the lower energy, there's always going to be an emission spectra, right? So if we calculate the differences in the energy, and if I suppose that an energy that is associated with the higher energy orbital, so we will take one case wherein an electron is jumping from second to first energy level, so we'll calculate in that case. So in that case, what will happen is this n will become n2, it's a higher energy orbit, and then this is the lower energy orbit, so it will be represented by n1. Okay, and if I say the energy associated with this orbit is E2 and the energy associated with this orbit is E1, so this E2 is always going to be higher, because we already studied that if an electron is away from the nucleus, there is more energy going to be associated with that electron, and when it's closer to the nucleus, there is going to be less energy associated with it. So E2 is higher than E1. This is already mentioned in my previous lecture. Now the difference in the energies, we already know the difference in energies is always going to be equal to E2 minus E1, right? Now if I calculate the frequency of the wavelengths that are being emitted at that point of time, so if this electron comes from here to here, there are going to be wavelength that is going to be released, or there is going to be an emission spectra or a spectral line. So now in order to calculate the frequency of that spectral line, I'll calculate it in CGS system first. So if we calculate this in CGS system, we know from our previous lectures, we know that energy is always going to be equal to minus 2 pi square m e raised to power 4 by n square h square. So in this case, the E1 is going to be n1. Here the n is going to be the n1. And in my previous lectures, I missed this negative sign for the energy of an electron, so I apologize for that, and I want you to include a negative sign wherein I calculated the energy of an electron in Bohr's model of an atom, because the energy of electron is always negative. And similarly, in case of the second energy level, what we are going to see is it's again the same thing. It's minus 2 pi square m e raised to power 4 by n square h square, but the n in this case is the second orbit. Now from this Max Planck's equation we know that this is again equal to h nu, and we know that the difference in the energies is equal to E2 minus E1. It's equal to delta E. So if I include the values of E2 and E1 in this equation, I'll get delta E equals E2 minus E1, or I have to subtract E2 minus E1. So that means I have to subtract minus 2 pi square m e raised to power 4 by n2 square h square minus again this equation, that's E1, that's minus 2 pi square m e raised to power 4 by n1 square h square. So upon subtracting these two equations, what we get is that delta E is basically equal to 2 pi square m e raised to power 4 divided by h square, and then 1 by n1 square minus 1 by n2 square. Suppose we keep this as equation 1. Okay, now we know from Max Planck's equation that this delta E is equal to h nu, so I can instead of delta E I can put a value of h nu in here. So I can say instead of delta E, h nu is equal to this equation that we obtained, right? Or in other terms, if I calculate this nu is the frequency of the energy that is given, right? So we have to calculate this nu. This is the frequency. We are calculating the frequency of this emission of this radiation. So if I calculate this nu, so this nu is going to be equal to 2 pi square m e raised to power 4 by h. Since this h comes here, so it's multiplied here, so there will become 3h, so 3 Planck's constant h3, and then the rest of the equation is going to be same, n1 square minus 1 by n2 square. Okay, so this becomes equation second. So if we put the values of these constants like pi, mass of an electron, and charge of an electron, the Planck's constant, the values, so this equation can be simplified to a very simpler equation that becomes I think the values that we calculate for this part, it's equal to 3.29 into 10 raised to power 15. So you can write 3.29 into 10 raised to power 15, and the rest of the equation same. And the units of this equation in CGS system are going to be per second, or it's going to be hertz. The frequency is going to be in hertz. Okay, and again this equation can be put in terms of SI, but before that, now since this equation was calculated or the calculations were done by Rydberg first time, so we represent this constant region by Rydberg's constant, that is represented by R. Okay, so it's this R is Rydberg's constant, and this constant here we calculated for the hydrogen atom. Okay, and the values that we have calculated here are in CGS system. Okay, now in SI system, if I calculate the same equation in SI system, this region is going to be changed, and in SI system the same frequency is going to be equal to m e is power 4 divided by 8 epsilon naught square h3 into 1 by n1 square minus 1 by n2 square. I think you have pretty much good idea about from a previous lecture where this equation comes in from. So this equation is in SI system, and the units are going to be different. So in this case the units are going to be different because the SI system is different and the CGS system is different. So now since we have calculated the equations in SI system as well as in the CGS system, we can calculate the frequency of the radiation that is released in case of this emission spectra. Now the another question is if we can calculate the wave number. Wave number is always represented by nu bar, and it's the number of wavelengths that can be accommodated in 1 meter. Okay, the number of wavelengths that can be accommodated in 1 meter. So wavelengths in 1 meter. is going to give us the wave number. Now this wave number, we know this wave number is equal to frequency nu divided by speed of light. Okay, and now if I want to calculate the wave number, all I have to do is I have to replace these values here. So if I say that I have to calculate the wave number or the number of wavelengths in 1 meter, so how I will do it, I know that this nu is equal to this value. So if we calculate it in CGS system, then we have to put in this value, and if we have to calculate it in the SI system, then this value. So in both the cases, what's going to happen is this nu value is going to stay there, and there will be an addition of C at the bottom. So in case of wave number, so there is going to be an addition of C here, and in case of wave number, there is going to be an addition of C here, and this is going to change to V bar. So this equation now becomes the wave number that we can calculate. We can also calculate the wavelength. We know that this wave number is equal to V by C, and it's also equal to 1 by lambda. So this wave number is inversely proportional to the wavelength. So if you are calculating wavelength, then you can put the values in here, or in simpler terms you can say that this is equal to 1 by lambda, this is equal to 1 by lambda. Then you kind of transpose the terms, and you get the value of lambda from this equation. You get the value of lambda in SI system from this equation. Now coming to the last part of this Bohr's model of an atom are the limitations that are associated with the Bohr's model of atom. So some of the important limitations that I'll be discussing here is that first thing is that Bohr's theory fails to explain the origin of spectra that are given by the multi-electron species, because all we studied so far in the Bohr's model is about the hydrogen or hydrogen-like species, that is helium, lithium divalent positive, beryllium trivalent positive, and all of these systems contain one electron only. So there's only one electron, and these equations are holding good only when there is one electron system. So this is one of the first limitations that is that the Bohr's model has. Secondly, the second limitation of Bohr's model is that according to Bohr's model, we always say that the electrons always revolve in circular orbits. So whenever we say that electrons always revolve in circular orbits. In other terms, Bohr says that the orbits in which the electrons revolve, they are always planar, or they are always in the same plane. But in modern times, I mean in nowadays, we know that electron doesn't revolve in a kind of planar orbit, and the orbits are basically three-dimensional in space. So orbits are basically three-dimensional. They go into x, y, and z axes. They don't stay in the electrons don't stay in particular planar orbits. They revolve like in different orbits around the nucleus. So that's also one of the important limitations of Bohr's model of an atom. And third limitation is that there is no explanation for the two effects that are also mentioned in the Rutherford's model of atom, that is Zeeman and Stark effect. So Zeeman and Stark effects, we already know what they are. When an excited atom which gives the line emission spectra, and whenever we put it in the magnetic field, its spectral lines are again split up into smaller, thinner lines, and these thinner lines are very closely spaced, and we call it as Zeeman. So in case of magnetic field, so the spectral lines that we studied, if I put a spectral line into a magnetic field, so suppose this is magnetic field, okay, so if I put a spectral line into the magnetic field, you will see that the spectral lines is divided into smaller, finer lines. The formation of these smaller, finer lines is not explained by Bohr's model of an atom, and this was first discovered by Zeeman. So Zeeman effect is not explained by Bohr's model of an atom. In a similar manner, if these spectral lines are put under the electric field and then observed under the microscope, you will see that these spectral lines are again divided into small, finer lines under the electric field, which was discovered by Stark. This effect was discovered by Stark, and Bohr's model of atom is also unable to explain why on earth these effects happen, and there is no explanation in the Bohr's model. Also, very importantly, I mean, so far we have been studying the quantum mechanical concepts of the atomic structure, and by the time Bohr's model was there, there was a revolutionary time that was going on, and the quantum instead of quantum, then came the wave mechanical model of an atom, wherein there was dual nature of matter that was included in there. I mentioned that Bohr said that the electron behaves as a material particle. Material particle. So but nowadays we know that electron not only behaves as a material particle, it also behaves as a wave. Okay, it also behaves as a wave, and this wave concept along with the material concept was given by de Broglie, who gave the dual nature of matter. And then at the same point of time there was Heisenberg's uncertainty principle. So Bohr's model basically cannot explain the dual nature of an electron. If we go to the Heisenberg's uncertainty principle, according to Bohr's model of atom, we always say that the electrons around the nucleus that are revolving in a particular orbit, in the circular orbit, they are always situated at a particular fixed length, right? So electron is always at a fixed length somewhere here. From the nucleus, and this fixed when we say that the electron is having a fixed velocity at some other place in a particular orbit, this goes against the Heisenberg's uncertainty principle, because we cannot say that electron is at some place and it has this velocity at that point of place, because Heisenberg's uncertainty principle says that there's uncertainty, you can with certainty know only the position, or with the certainty you can only know the momentum or velocity of an electron. So in an overall, these are the important limitations that the Bohr's model had. It was unable to explain the line spectrum for the finer lines that are in the line spectrum, or the finer structure. It was also unable to explain the dual nature of an electron that is there. I think this is pretty much clears my Bohr's model of an atom. I hope you guys have liked my previous lectures also, and this lecture also. And if you like our work here, what we are doing here, so please subscribe to our channel and do share.